Welcome back, everyone. Thank you for coming to the afternoon session for the short talks. The first one is going to be Elzbieta Polak, will be telling us about geometry and optimization of shallow polynomial networks.
Thank you. Hi, everyone. My name is Ella, and I'm a PhD student here at UT Austin. And the talk I'm presenting today is based on a paper called Geometry and Optimization of Shallow Polynomial Networks. It's joint work with Yossi Arjevani, Joan Bruna, Kileel, and Matthew Trager. So our model considers a single hidden layer, so as opposed to the schematic where we have 3 hidden layers. And so if you feed a data point into this network, this is the mathematical representation of what's going on there. So we have parameters of the network, alpha sub I, w sub I, data is x, and then r is an important parameter because it's the width of that single layer, that single hidden layer. And we are considering polynomial nonlinear activations. So the degree of the activation is d, little d. And this model was first considered in 2019 in a paper by Joan Bruna, Kileel, and Matthew Trager. Now, all the neural networks of this form a functional space. We call it calligraphic f sub r. And this is a semi-algebraic set. So now if we remove the data for a second, we can consider this parameterization map tau that goes from the parameter space to this functional space. And so just by looks of it, maybe it's somewhat obvious that those functions in f sub r can be identified with symmetric tensors of rank r. And furthermore, if you're given 2 points in the parameter space, like this calligraphic w, calligraphic v, those points uniquely identify a function in f sub r. Okay, so we bring the data back. Consider capital N pairs of the form x sub I, y sub I, coming from some distribution capital D, where we are looking for a functional relationship between the x's and the y's. We assume such a relationship exists, and we are using our neural network to precisely find it. So basically, it is done by means of empirical risk minimization, as you're seeing here. But when you have many, many points, if capital N is very large, then it's very close to the population loss. Okay, so this is the formula for the population loss. And now I think it's going to be informative to kind of go over this computation of the population loss. Okay, so if you go through expanding and simplifying several times over, you end up with this sum of inner products, where the second term of each inner product is this higher moment tensor, is the stuff in red. Okay, and so it's precisely the 2D moment of the data distribution. Let's call it capital M with some subscripts and superscripts. And we will use this 2D moment of the data distribution to define an inner product. So consider 2 tensors, capital T, capital S. We define the following inner product, where we flatten the tensors. We vectorize the tensors, and we flatten the 2D moment tensor. So basically, we get some like quadratic form. And this inner product induces a pseudo-norm. And this pseudo-norm we will apply to our functional space. And the reason we do this is the following theorem. So let M be this 2D moment tensor of the data distribution capital D. The population loss for a polynomial activation function of degree little d with samples from capital D is given by the squared distance function with respect to this non-standard inner product, namely inner product induced by capital D. Okay, so this was a mouthful. Let me try an easy example here. So suppose we have a really silly little neural network with a single neuron. So the width is 1. W weights come from R2. Alpha weights are just 1. And so if you expand the formula I gave you first, you get those 2 functions. And then if you compute the population loss, you end up with this expression that has those those fourth moment coefficients, all the stuff that's highlighted here. Okay, and so those are precisely the entries from a four-way tensor. And there are 16 monomials in x1, x2, such that the exponents add up to 4. So the theorem was saying that basically you can express this population loss that I just computed using certain quadratic form, right? So this is the quadratic form in question. Okay, so now you may ask, well, do all quadratic forms come from some data distribution? That would be very, very nice, but the answer is no. And the counterexample is actually the Frobenius inner product. There does not exist a distribution such that the Frobenius inner product is a flattening of some 2D tensor. And this is the first time when we see the Frobenius inner product being somewhat special. Okay, so here I have one example for what the inner product looks like for one concrete distribution. Namely, if you consider central Gaussian distribution with IID coordinates, then the formula for the inner product is given in terms of trace of several different matrices and in terms of the second moment of the distribution. Okay, so now let's talk about the critical points of this loss function, and we focus on quadratic activations. So basically, we focus on the matrix case, where the tensors are matrices. You may recall the Eckart-Young theorem that says that for the Frobenius norm, the number of critical points of rank R approximation of a symmetric matrix comes from the eigendecomposition of that matrix. And furthermore, the number of solutions is n choose R. So we have an extension of this theorem for the case of the Gaussian inner product. Namely, the critical points again come from the eigendecomposition of the symmetric matrix that you are approximating. As you see, the formula is quite a bit more complicated. For the diagonal matrix in the middle, this capital lambda sub RII. And I'm not going to explain the details. The important part here is that, again, the datum for this is exactly the same. The eigendecomposition and the number of critical points is the same. So now you may think that there is some underpinning principle that says that any low-rank approximation, no matter what the weight is, maybe has something to do with eigendecomposition. Maybe it's always this number of critical points. Unfortunately, that's not the case. There exist matrices, symmetric matrices and distributions, such that the number of critical points for rank 1 approximation is exponential in n, 3n minus 1 over 2. So we have a negative result on that. Okay, so what we generalize this? We always vectorize our tensors, and we just consider some general inner products. So some matrices of the size n squared by n squared. And furthermore, remember we had this functional space of tensors. Why don't we take the Zariski closure of this guy, call it capital X? And the reason we would do so is that then we can use the methods of algebraic geometry, which is the second part of my talk. Namely the Euclidean distance framework. There is a trade-off here. If your activation is larger than 2, the degree of the activation, then the Zariski closure actually makes the space much, much bigger. However, at least we get those other tools that we can talk about. So let me introduce some notation on this. Approximators, for example, low-rank matrices, is what we call students. They live on the variety X. Matrices that we are approximating, or tensors that we are approximating, we call them teachers, so that students approximate teachers. And then for the weight matrix, we use either capital W or lambda. So basically, we have this setup, student-teacher setup. Okay, so I promised that I would introduce this algebraic framework here, so let me do that. So there is this thing called the ED degree, Euclidean distance degree, and it was introduced by Jan Drysma, Bernd Sternfels, and other researchers in 2013. this is the definition. So the ED degree is the number of complex, smooth critical points on your variety, capital X, of the real distance function in n-dimensional space. So this is important that your solutions could be complex, but the distance function is real. We don't take any conjugates. And which kind of comes from the Lagrangian formulation of it is that those different vectors, t minus s, are orthogonal to the tangent space to your variety at one specific student matrix. This is how it looks like. So here we have a variety consisting of two blue curves. So this is the student variety. The teacher is the point in the middle, and the ED degree is 8. We have 8 solutions, and if I were to draw those tangent lines, you would see the tangent lines are definitely orthogonal to those red lines. The black lines is the global minimizer. Okay, so now our setting was that we had those weighted inner products, right? So let's introduce this into this mix. And so the formula I'm giving you here, the weights are those lambda sub I. Because of the weights, we don't have usual orthogonality, we have some lambda orthogonality. This setup here, in terms of like a quadratic form, would correspond to a diagonal matrix, diagonal weight matrix. And this is a very popular definition in the ED degree community. We, in our paper, consider more general weight matrices that are dense. And I will show you an example of it later. And this was considered in several papers that I listed here. So one interesting thing about the ED degree is that depending on your weight matrix, you get a different number of solutions. In other words, the ED degree is different for different inner products. As you see, for the Frobenius, the number is much smaller than for general weight matrix. In fact, those degrees you see in the first row precisely come from Eckart-Young theorem. So our idea here was to include the weights in the algebraic description of the problem. So this is what I'm going to do next. So my starting point is the normal bundle, which also in this context is called the ED correspondence. So suppose you have some variety, capital X, of codimension C. A variety is defined by its ideal, capital I sub X. And suppose T is a generic point in the ambient space. Then the ED correspondence is an n-dimensional variety that has this vector bundle structure. So you can either project onto your students or you can project onto your teacher. Right? And so you can imagine that it's basically, if your variety is some geometric object, then you have fibers that are perpendicular to the tangent planes to the variety. And this is the ideal of this guy. As you see, it involves the ideal of the variety itself, but also this big term in the middle, those minors. This is precisely the orthogonality condition that makes sure the fibers are orthogonal to the variety. The second part of this definition basically tells us that we exclude singular solutions. So we extend this notion by adding the weights. So we have not 2 but 3 projections. As you see, the last projection is onto the set of symmetric matrices, which corresponds to the weights we are using. And we incorporate those weights into the definition. Okay, and the last concept I wanted to introduce today, and it's actually fairly important, is the ED discriminant. So let me quickly explain what's going on here. In that normal bundle or ED correspondence, we single out a subvariety called the ramification locus, which consists of points where the differential of the distance function is not full rank with respect to the students. So you have less than a generic number of solutions, basically, to a distance function. Now, if you take this ramification locus and you project it down onto the space of teachers, then you get the discriminant. This is a classical example of the discriminant. So the variety of students is this red cardioid. Generically, for any teacher in the 2-dimensional space, you have 3 solutions, 3 critical points of the distance function. But if your teacher lives on that green small cardioid, then you actually get only 2 solutions. One of the solutions comes with multiplicity. and again, because we are incorporating the weights into our description, we extend this notion. And so what happens is that we have a larger sort of space for the second projection. We have a joint space of teachers and weights, symmetric matrices. So now I'm going to give you an example, a very simple one. So suppose we have a 2x2 symmetric teacher matrix and want to approximate using rank 1 matrix. This is an algebraic condition given by the vanishing of the determinant of this matrix. So the discriminant in this case is hypersurface. The ideal has degree 6 in teachers and 8 in weights. It has 34 terms. And if you project onto teachers, you get the usual discriminant. But before us, I don't think anyone considered the degree in weights. I think our setup is kind of the first one of that sort. So this is how this polynomial looks like. So lambdas come from the weight matrix. T's come from the teacher matrix. Please try to memorize this polynomial as we will need it for the next slide. Okay, what's happening here? If I take one concrete teacher and plug this teacher into that polynomial, and then furthermore, I fix one of the weights in the weight matrix, I only have 2 degrees of freedom left. In other words, I can plot this discriminant like a slice of this discriminant in the weight space. So those curves you're seeing here, this complicated shape, is precisely the discriminant, the slice of the discriminant. So what's interesting about this picture is that you have this dot there. Okay, so this dot has coordinates 1, 1. If you combine it with the fact that one fixed weight is also 1, then this dot signifies the Frobenius inner product. And it shows you that the Frobenius inner product is not on the discriminant. And by the way, so those curves basically slash the space, they partition the space into those connected components that are called discriminant chambers. Okay, and so discriminant chambers are quite important in this, and I will explain it in a moment. Okay, so we have this theorem. The extended ED discriminant of a smooth complex projected variety X is a hypersurface unless X is linear. And I told you I would give you an example of the discriminant when the weight matrix is dense. So this is precisely this weight matrix coming from the Gaussian distribution, Gaussian IID distribution. And so it turns out that in that case, the by degree of this polynomial is 6, 12, 6 in teachers, 12 in weights. And the polynomial has over 2,000 terms. It's really massive. Okay. Now, if we only consider the real part of the discriminant, this is what I was talking about before. It's partitioning the space. We have those chambers. And so we have this theorem about those chambers. So the number of real critical points, S, and the signature of the Hessian at each S is constant in a connected component of the complement of the extended ED discriminant. And this is very useful for the following reason. I'm not sure whether you're aware of this or not, but as soon as you're using a non-standard inner product for your low-rank approximation, the problem becomes NP hard. There are no closed-form solutions. However, if you know that your inner product lives in the same chamber as, for example, the Frobenius inner product, you can apply homotopy continuation method so that your start system is Frobenius, your target system is precisely the system you're trying to solve, and you can trace the homotopy path, and so the solutions of the Frobenius system will take you to the solutions of the other system. And we did perform those computations. It really does work pretty well. Okay, so I would like to summarize what I shared today. In our paper, we show that the training of polynomial neural networks motivates low-rank approximation, and those weights come from basically your data distribution. We have an analog of Eckart-Young for the Gaussian-induced norm. We extend the ED degree framework and show that this extended discriminant surface controls the landscape of the optimization problem. And if you guys liked it, consider scanning this QR code. It will take you to the paper. Thank you very much for your attention.
Any questions?
Is there any relationship between this work and this paper by Satan Chen and Raghu Mecca about learning push forwards polynomial activations? Like they're basically trying to learn polynomials and trying
There may be a connection. I'm not aware, but if they are working with polynomial activations, then I'm sure that we could draw some connections.
Okay, I can show you the paper.
Sure.
Okay, let's thank Ella.